Hello everyone, my name is Abhishek Bansal. In this video, I am going to talk on the buck boost converter. I would be taking the transformerless or a non-isolated buck boost configurations, inverting and non-inverting both. In another video, I am going to take the transformer isolated buck boost converter, which is basically a flyback converter. So the flyback converter, it has its roots in this non-isolated buck boost only. There has been some confusion, and I have made even written a blog on element 14 flyback quandary, whether it's strictly a boost converter or a buck converter or strictly a buck boost converter, because we have found that the flyback transformer has been used in applications where it has been used as a strictly a boost operation. And even I have designed the 72 transformers that I have mentioned some method I have claimed. So for that also the transformer has been used as strictly step down. There are more points to this flyback quandary on a strictly a buck or a strictly a boost or strictly a buck boost converter that I would be summing up in a separate video. So for this I am going to talk on the buck and boost operation, the derivation of the converter, the mathematical operation, the continuous mode operation of the buck boost converter. But the reference of the flyback quandary I mentioned here in this video, because the same principles are followed in the transformer isolated flyback converter, because the flyback converter is basically derived from this buck boost only. And when it forms a buck converter and when it forms a boost converter or it's a buck boost converter, how a single transformer can act as both the step up and the step down, because when we are talking of a buck, we are talking of a step down. And we will see that if the input, the universal voltage, that's basically a 230 volt AC, or if I translate it into DC, 325 volt DC, 325 volt DC, that is a 325 volt DC. If I am taking a 325 volt DC, I am stepping it down to a mobile charger, which is basically a 5 volt DC. So I am already taking a 320 volt DC reduction here. And if there are some engineers who have classically used in the old old color TVs or the CRT cathode tubes, they basically essentially use up to 10 kilovolts or even the 35 kilovolts, and that was have been even a flyback operation only. That was even a flyback converter only. So why is it's not called a boost converter when it can be very easily called a boost operation? Because it's a 35,000 volts and it's a 5 volt. So there is a tremendous difference between, there is a very big difference, and all these points I would be summing up in a separate video of the flyback quandary. The point of mentioning it here is when a flyback operates as a buck converter, how we can use it as a boost converter, because we are having a physical transformer, because we know that it all depends upon the number of turns. If the number of turns are more, or we can make it as a boost operation or a step up operation. And if we are going to decrease the number of turns, we are going to get a step down converter. But we have we have some small transformers. How can the number of turns are already fixed, I cannot change the number of turns when I have a physical product there. Then how it becomes a buck converter and a boost converter? Why it's a buck boost converter? The main point would be, one of the main points, not the main point exactly, one of the main points would be concluded in this video or a lecture at the end. That's why I mentioned the flyback quandary that I would be explaining later on, because there are many points in that. So one point will be taken from this video. So let's start with the buck boost thing. The buck boost is basically derived from the cascading of the buck with the boost. That means if I am going to say if I am going to design it by a SPDT or single pole double throw, I can say this one position switch, two position, and this is the inductor, this is the capacitor. Here again I am taking all the DC only. I am not taking an AC to DC. DC I am talking of. That means I am expecting the operation, or I am expecting the input source to be a DC. It can be AC to DC, because I am going to explain the mathematical operation in this. The mathematical operation would be related to DC to DC. So this is a buck converter. I have already explained it, and we know that V output by V input relation is basically a duty cycle D, and this is basically the conversion ratio M of the D. Now if I draw SPDT, the boost converter, we have an inductor here. Okay, we are having an inductor here, and this is one position, two position. This is a boost converter. So in this, if I draw the graph has to be linear only. If I am going to draw with respect to the conversion ratio and the duty cycle, it will be obviously a linear passing through the zero. Here the graph is not linear, it rises like this way, it do not start with zero. Now I would be cascading both these converters, buck along with the boost. Here the conversion ratio was 1 upon 1 minus D. Okay, we will soon see that if I am going to drive a buck boost configuration, that would be having an polarity of minus, or known as an inverting buck boost converter. If I put an inductor here, and this is a two position, this is one position, this is here, we see that this will have the conversion ratio of minus D upon 1 minus D. I will derive the circuit configuration also, I will derive this conversion ratio also, I will also explain the continuous conduction mode mathematical operation also. Just for a brief, I am just want to bring into notice that this is the duty cycle axis, this is the conversion ratio axis. That means here, because of this negative, it's falling down. Okay, this is a minus of an MD only. And if I am taking a non-inverting configuration, that means I am getting the conversion ratio as positive. In that scenario, the circuit configuration would be this way, 1, 2. Okay, in this scenario, this is a non-inverting configuration, therefore it's the conversion ratio D upon 1 minus D. Instead of this thing, it would be rising here. The difference between the boost and this would be, it starts from here 0, it do not start here from 0. Okay, so let us first go into the derivation of how the buck boost configuration is cascaded, and we get this circuit now. So we know that we can very easily see that this is our buck converter. This is the position 2, this is the position 1, this is an inductor, this is a capacitor. So this is our buck converter. Let me draw it more neatly. And we have a boost here. One, two. this. So now we are just connecting it, and this forms a buck boost converter, and this is basically a non-inverting configuration, and you can see very easily here that we can denote the L1, C1 for the book converter, L2, C2. I have only attached them, I haven't done any of the changes yet. We can see this particular thing is forming a 3-pole low pass filter, whereas the motive of again the buck boost converter is to provide an regulated output voltage only. It can be step up or it can be step down. So it's a 3-pole low pass filter, and we do not require especially the number of poles. It's not that if we are going to increase the number of poles, we are going to get a better conversion ratio, because the conversion ratio do not depend upon the number of poles, and therefore I can safely remove this filter here, C, and if I remove this filter C, what we have got, we are getting here this thing. Let me draw the similar to that only. So we get now 2 inductor in series. Okay, we are getting 2 inductor in series. So this is a 2 inductor in series, and this is a position 2, this is position 2, this is position 1, and here we have a filter capacitor. Now these 2 inductor in series, and we can even combine it and replace it by what? 1 inductor. Okay, we can simply replace it by 1 inductor. So now we can get different kind of sub circuits depending upon to choose whether we are choosing the position 1 or a position 2. If we see in this position, I have used a single pole double throw. That means we can use 2 ST switches also. That means 2 switches are here, 2 switches are here. It forms a 4 switch configuration. That's why this buck boost converter is also called as 4 switch configuration converter. Now I am taking this basically a non-inverting configuration. Now we first play with this position, the switch positions. I am going to play first with the switch positions. If I am going to choose the position 1, that means now let me draw some input source also, because it will look as an open circuit. It's not an open circuit here. We have an input source here, V input we are having here, and we are having some, say the, okay, this is the load. This is the load. Okay, so when we are taking a position 1, we will see that we will add the input. We are going to have this V input. This inductor would be here, and the direction of the current is this. This is the dot point here. This is the capacitive filter, and again the load is connected. This is the position 1. If I am going to do with the select now the position 2, it's obviously the input would be what? Input now is going to be open, plus minus is going to be an open input, and the inductor is going to be directly connected with the load. Earlier here the inductor is connected with the source, input source. It's similar like a boost operation only. Okay, now the inductor is connected to the load, it's connected to the source, and here we are having a output. So this we have got that the energy is transferred in this position 1. The energy is transferred from input source to the inductor. Okay, and here the inductor is connected to the load, and energy is transferred from the inductor to the load. Now if this is a non-inverting configuration, if suppose I want inverting configuration, I have to just change the switch positions, and that too we can very easily achieve it using a position 2. If I choose the position 2 here and reverse the inductor connections, that means because here the current was flowing in this direction, now for reversing the output polarity, I will take the inductor polarity, inductor like this way. Okay, earlier the dot was here, it was going in this way. Now the dot of is here and it's going inside in this way for the inverting output voltage. So now let's derive the, we can very easily see that if once we are connecting it, what we are basically getting is that we have basically cascaded the buck and a boost, buck followed by a boost. Now if I recall, in the buck video I have mentioned that the buck is basically an equivalent DC transformer. That means I can have a equivalent model with the 1:D transformer ratio, and let's say for the boost it's D dash, not D dash is to 1. That means excuse me, here. So we are having a transformer. So this circuit is going to inherit the properties of both. What property it is having? Both are having a pulsating current property. Here the difference is that here the pulsating current is the input current, and here the pulsating current is the output current. So it's going to get the properties of both of these, and this basically finishes our circuit configuration, derivation configuration of a boost buck. Now let me also derive the conversion ratio formula also. The conversion ratio is again a very simple thing, because we know the conversion for the, if I take the buck converter, the conversion is V output upon V input is D. For the boost we know the conversion ratio is D 1 upon 1 minus D. So once we are basically cascading it, multiplying it, we are getting this thing only, D upon 1 minus D. In very simple way we can say this is the conversion ratio of the buck boost converter. And let's go now to the mathematical operation of the buck boost converter. And like in the buck converter and the boost converter, we have made several assumptions. We have made the periodicity condition to be there. Similarly, we for analyzing these non-isolated transformer-less buck boost converter, we are going to make the same assumptions, that the circuit is operating in a steady state. The inductor current is continuous, because I am going to talk the continuous current mode of operation. The capacitor is going to be large enough, while we are going to have used the practically finite capacitance, and the switch is closed for a time duration of a dt, and it's going to be open for 1 minus d into t. This is going to be t of time, and the most importantly, all the components are idle. We are not assuming any of the non-idle conditions. So let us again draw buck boost converter. Now we know that the buck boost converter, if you remember, I have in a 2 switch position, I have said this is 1 position, this is 2 position, this is an inductor, and this is a capacitor. So this is a buck boost converter, which is an inverting buck boost converter. Okay, the 4 switch converter can be simply a what? It's simply a non-inverting. You remember, in the buck inverting, the inductor was here. That's what I said. I am changing the inductor polarities, and we are going to get a inverting configuration. So let's take this inverting configuration only, and in this inverting configuration, now instead of 2 switches, I am using one as a switch, and another I am going to mention it as a diode. So we are having a switch here. Okay, I can draw this. We also switch for this, we are having an inductor here because I am taking an inverting configuration, and the others, instead of SPDT or SPST, I am drawing a diode here and again the filter. So this is a buck boost inverting circuit, and when this circuit is going to be closed, this would be an open, and when this is going to be an off, this would be connected to this thing. Okay, so when the switch is closed, okay, now let's say when the switch is closed. So when the switch is closed, if you remember, I have drawn it like I have drawn it this way. This is the closed situation only, because this is going to be reverse bias, is going to be open. And in this, if we see, this is an IL which is going to flow across it, we can say it's an VL voltage, and that would be equal to the input source. Here we are assuming we have some voltage requirement, that's in V output here. So what we have got here, when the switch is closed, the voltage across the inductor is basically the input voltage, and again it's an L di by dt, the similar way of the buck and the boost thing. Okay, so we can put L here, and that is the rate of the change of the current. That means di would become delta IL upon delta t. We know delta t is closed for how much duration? Dt time duration. So it's basically the very similar way we have got a delta IL during the t on time, or the closed time, we can say, is basically what? V input by L into dt. So this is our one equation for the during the time when the switch is open. Now let's say the switch is so now let's say the switch is open. So when this switch is open, what we are left with, it would be like this way. We were having an inductor here, and we are having a capacitor here, because this would be shorted, and this is the DC input and the DC output here. So now if we are going to write a mathematical operation, we can again say this VL is definitely equal to what? V output, and this is again going to be L di by dt. Again similarly I can put L here, this di again I am to go to delta I upon delta t. Now we know that it's off for the time what? 1 minus dt. All this time duration on and off had been similar for the buck boost, all these modes and all these configurations. The switching time cycle is the dt and 1 minus d into t. So we can basically get very easily, we can find here the delta L is what? V naught upon L into 1 minus d t. Okay, and again as we are taking a steady state operation, we will say that the delta I during the on time and the delta I during an off time, or the delta I close and the open is going to be, the summation is going to be equal to 0. So that is now equal to 0. So we are going to again equate it. It means delta I L on plus delta I L off equal to 0, and I am going to put the values that we have got it. V input dt upon L plus V output 1 minus d t upon L equal to 0. This L will go, now we will be left with 1 minus dt plus V naught 1 minus d equal to 0, or V input dt won't be here because t will get cancelled, plus V input minus Vd, or we do not need to expand it, simply we will take this plus it here, minus V naught 1 minus d, or we can say V naught upon V input is d upon 1 minus d. So one simply I have derived from the cascading principle, that if we are cascading it what would be the d and the 1 minus d, and this is the mathematical derivation, longer derivation, if we are going to consider the inductor voltages, inductor current, sorry. Okay. So what would be the required duty cycle then? We can say the duty cycle is going to be required V naught upon Vs or V input plus modulo of the V output. I have taken the modulus. Why? Because here we have the inverting configuration and the non-inverting configuration, and if I by mistake take a non-inverting or inverting configuration, this would be the minus, and it's going to make the calculation, going to give a calculation error. So I have taken the modulus, and we can say that the average inductor current is going to be 0 for the periodic operation. Now the main important thing before closing this, okay, I will be doing it later on only. Firstly, let me complete with an output voltage equal, and also let me take the current and the voltage relations. Okay, so we know that our it's being a continuous conduction mode, on is going to be ramp up, it's never going to have a 0. These peaks are all similar, it's an I max, and here we are having an I minimum here again, and I can similarly say that the inductor voltage is would be this way. Okay, so now let us take a diode. The diode current would be also during an off, it will off. This thing, the diode current would be this thing, because it's a periodic. Okay, now the capacitor would be, the capacitive current would be this. Again, this is the delta Q. Okay, so we are having a, now here we can say we need to see that this is the diode current, and in this diode current I am taking a, this is a diode current line, this is a time axis, this is, if this is dt, this is t. So what if I draw this line in between here, it would be an id, and that is equal to V naught by R, because I have taken a resistive load. That means if I am going to say the power absorbed must be the same as supplied by the source. If I am going to consider only the ideal circuit, that means input power is equal to an output power, I am going to get it, the PO is equal to V square upon R, output voltage, and it's going to be equal to V input, I input. Okay, now we know that the average source current is related to what? Average inductor current by what? IL D equal to the IN. We can put an value of an IN, this thing here, and it is going to get V square naught R is equal to V input IL D. Okay, so we can use now equation. The conversion ratio which we have got, that is d upon 1 minus d. If I am going to use that d upon 1 minus d, so we got what here we are getting an IL equal to what? V naught square. Let's take V input here. V input here would be there and D would be here. Okay. From this we can get. If we put what is the value of V naught, we know what is the value of V naught by V in. So we can say it's V naught R V in D, and the value of this V naught V input we can put what? D upon 1 minus D, and here D already we have, this is an R, so we got V naught upon R 1 minus D. This is an average inductor current in the buck boost converter. Have I done somewhere mistake? Yes, because it has to be square. Now let us again write, because if the mistake was that this would be equal to IL would be equal to, I have taken in the output, it was not a mistake, it was in terms of an output. Now let's take in terms of the source current. So if I have to take a instead, this is the equation we have. Now if I have to say what is basically B, this is basically equal to what? D upon 1 minus D. And if I have to write in terms of V input, this implies V input is what? V naught 1 minus D upon D. Okay, we can put this here. Okay, and once we put all these things here, we will get an IL equal to V input D upon R 1 minus D square. Okay, because, or simply we put it here, na? Simply let's put it here. Instead of complicating this, V naught we get from this thing equal to, put the V naught here, it will become D square 1 minus D the whole square, V input the whole square, and let's put it R V input D. So 1 D will get cancelled, it will remain 1 minus D square. V input will get cancelled with this 1 V input. So that is why it's a V input D. V input D, we are having an R 1 minus D square. So it was not wrong, it was in terms of an output voltage. If this is in terms of an input voltage, the average inductor current. So similarly we can get a maximum inductor current. We can similarly get a maximum inductor current or the minimum inductor current, that an I minimum or an I maximum would be related to an IL plus, sorry, I max equal to IL plus delta IL upon 2 in the case of maximum. In the case of minimum, this would be the minus sign, and we can very easily put the value of an IL, because IL we know very well what, it's V input D upon R 1 minus D square plus what was the delta IL, it was V input dt upon 2L. So this is the maximum inductor current, and for the minimum we are going to simply put a minus sign here. Okay, and like the we have mentioned, the boundary condition would be existing when an I minimum equal to 0. Similar in the similar fashion like the buck converter and the boost converter, the I minimum 0 is the boundary between the continuous and the discontinuous mode, and we are similarly going to get the LF minimum would be equal to 1 minus d square R upon 2, because this is the minimum current and this is going to be equal to 0. That means these two both are equal. Now this d will get cancelled. Let put T by 1 by F. This is LF. Okay, this input is again going to get cancelled. So what we get, if we just rearrange it, we are getting LF here equal to 1 by 2. Okay, this R, and we will take up here R 1 minus d square. So this is the expression that I have got here. This is the minimum level or minimum inductor current that should be there to avoid going it to the discontinuous mode, because this is a continuous mode of an operation. Now the last thing that was left is basically a capacitor, and the capacitor would be analyzed in the same manner only. If you remember, I have drawn a triangle, and in the boost I have drawn a rectangle. I have taken from the graph and put the value here. We will see that the IC is here, and this would be, this is the area delta Q. Okay, this delta Q is the area. So the area of the triangle is the length into breadth. We will see that this delta Q, Q is equal to CV, again the same formula, and this is basically what, V naught by R, and this is what, dt. So we can very easily say this delta Q is equal to C delta V naught, that is the output voltage ripple, and it's basically equal to what, V naught by R dt. Or we can if we take these two equations, we can very easily say that delta V naught, that is then ripple, peak to peak variation of the ripple voltage, it's V naught by R. Okay, d, T we can put as 1 by F, frequency we have C. So this is the, and if you have to take with respect to the as a fraction of an output voltage, we can take V naught here, and the expression would be this thing. Okay, and again in terms of because the capacitor is going to have an ESR, and the ESR of the capacitance itself significantly causes what, output, which it affects the output voltage ripple. So the peak variation in the capacitor current would be same as the maximum inductor current, similar like our previous boost converter configuration, and the theory of operation is similar in that manner only. And we can say that an delta V naught and ESR is going to equal to what, delta IC R dash I have put there, similar way here dash, and this delta IC is the IL max. So it's the same expression only. Okay, so this concludes the output ripple voltage current relationship. Now the most important thing, why it's called a buck and a boost converter. I have mentioned that the excuse me, the transformer ratios are going to be fixed in a particular physical product that I am going to handle a buck boost converter. So how it's going to operate it? The answer to it lies in that we are going to variate the duty cycle. We know that the V output upon V input is equal to D upon 1 minus D in the case of the non-inverting. So when we have basically, when the duty cycle is greater than 50%, or if I say the duty cycle is greater than 0.5, the duty cycle greater than 0.5, it's a boost operation. It's a boost operation, and we are basically getting an output voltage greater than the input voltage. If I take a duty cycle less than 50%, or if I take the duty cycle which is less than 0.5, then we are getting a buck, or we are getting a output voltage which is less than the input voltage. So with the physically the same number of turns fixed, we can make it to run either as a buck operation or a boost operation depending upon the duty cycle. And this point is the would be used in the flyback counter video, because we can use a flyback transformer as a buck boost, because it's derived from the buck boost only. We can make it to work only in the strictly a boost configuration or and also in the buck configuration. So thank you.